Hi everybody, this is our first video covering section 2 of chapter 3, and here we are going to continue our discussion on numerical descriptions of data by talking about measures of dispersion or measures of breadth or width. In section 3.1 we talked about finding the center. In this section we are going to talk about how much the data varies about that center. The larger dispersion, the more variable the data is. The less dispersion, the more tightly the data is to the mean. And we are going to talk about 3 of the 4 measures of spread here. The first one is the range. The second one is the variance. The third one, which is closely related to the variance, is the standard deviation. And the fourth part, interquartile range, we will reserve for section 3.3 because we need information there to actually define that. Okay, well, if we want to talk about the spread of the data, probably the most obvious thing we can do is take the largest data value, which here happens to be 5 in this data set, subtract it from the smallest data value, which in this case happens to be negative 35, and that tells us the range of our data set. So this is perhaps the most trivial, straightforward way to determine dispersion. Take the largest value and subtract from it the minimum value. In this particular case, the largest value is 5. The minimum value is negative 35. 5 minus negative 35 is just like 5 plus 35, which happens to be 40. Notice that our dispersion will always be a positive number. It will never be a negative number. If it happens to be 0, that means that every single number in your data set is the mean. Speaking of the mean, the next measure that we want to talk about is the variance. Now the variance measures the spread of data relative to the mean. Notice that it's different than the range. The range has nothing to do with the mean. It's just the largest number minus the smallest number. Here we want to compute the distance from every single data value to the mean, and we want to use that to compute the average squared error or average squared distance. So what we're going to do, is take every single data value, find its distance from the mean, square it, do that for every value, add them up, divide by the number of data points, and you have your variance. Now notice that we have 2 variance measures. The first one is the population variance, and it is given the symbol sigma squared. Now the next type of variance is the sample variance. Now keep in mind that the sample variance is computed using a sample of the population. As a consequence, the sample variance is an estimate of is an estimator or an estimate of the population variance. It is given the value s squared, and since it is an estimator, there are a couple of parameters that we need to talk about which have to deal with the quality of an estimator. Those parameters happen to be called bias and efficiency, and we will talk about that in just a moment. First thing is, well, how do you compute the variance? Let's start off with the population variance. Remember, the variance is the average squared distance between each data value and the mean. So what do you want to do? You want to take each data value. You want to subtract it from the mean. You want to square it. You want to do that for every single data value, which is kind of like what we're doing here. And notice this is the shorthand version using the symbol sigma, in this case big sigma. And once you've summed them all up, you want to divide by n, which is the size of the population. Okay, pretty straightforward. What about the sample variance? Almost done the same way. The idea is still the same. We want to take every single data point and compute the distance between between each point and the sample mean, not the population mean, because we probably do not know what that is. We want to add them all up, which is kind of like what we are implying here with our summation operator, also known as big sigma. But now instead of dividing it by n, the sample size, we want to divide it by n minus 1. So notice here, we're adding up all the square distances, we're dividing it by the size of the population. Here we are adding up all the square distances relative to the sample mean, and we're dividing it by n minus 1. Sounds kind of weird. Why in the world are we doing that? Well, it has to do with the fact that this right here, the sample variance, is an estimator of the population variance. And when you are evaluating estimators, we use two metrics. The first one is called bias, and we want our estimator to be unbiased. What does it mean to have an unbiased estimator? Well, suppose that we have a whole that we take many samples of a population, and for all of those samples, we actually compute a variance. Well, then the estimator is unbiased, and the average of all those sample variances should be equal to the population variance. Okay? The other one is efficiency, which basically means that the more samples you take, the smaller the closer the sample variance should be to the population variance. Now, if it turns out that instead of dividing by n minus 1, we divided by n, lowercase n, let me see if I can draw that without hurting myself. Doing this on a drawing pad or drawing tablet can be a little tricky. Then this would be a bias estimator. In other words, if we took if we took different collections of samples and computed, and for each one computed a different sample variance and averaged all of those sample variances, we will actually get a number that is less than this. Okay, which basically means it is biased. On the average, we want this to be equal, which will not be the case if we divide by n. So this basically, if we divide it by n, we would fail this particular criteria. We still have a small error, but it's going to be a small error to the wrong value. How do we fix that? Dividing it by n minus 1. It can actually be showed using an operation called the expected value, that if you divided by n, this estimator would be biased. However, using the same approach, using the same concept of expectation, which is beyond the scope of this course because it involves a little calculus, if we divided by n minus 1, then our estimator will no longer be biased. So that's pretty much why we divide by n minus 1, because it provides us with an unbiased estimator of the population variance. How do we compute the sample variance or the population variance? In this case, we're going to do the sample variance first. And notice that we have a 4-step procedure if you need to do this by hand. Okay, and here it is. Well, the first thing that you need to do is you got to compute the sample mean. Okay, so that's step 1. Step 2 is we need to compute the distance, the squared distance between each data point and the sample mean. And this is kind of best done using a table. So here's my table. I have each data point here. I have the sample mean, which we've just determined is 14. And we know how to compute the sample mean. I kind of blew through that. We take our numbers, we add them up, divide by the number of numbers, we have 14. Okay? And then we just compute the distance, and then we square it. So 15 minus 14, 1, squared is 1. 12 minus 14 is negative 2, squared is 4, and so on. It should be relatively straightforward. Once we've done that, we add them up. Turns out all this sums to 10. And after we figure that out, we divide by n minus 1. Since n is 5, n minus 1 is 4, and our sample variance is 2.5. What about the population variance? Practically the exact same thing, except now we are dividing by n. Now keep one thing in mind. This is the sample variance. So this is the sample variance, where this is a sample of a potentially much larger population. And so this right here is an estimator of that population variance, which hopefully is somewhere around 2.5. However, in this particular case, this is the population. This right here is the population variance, whatever it turns out to be. So there are two different things. One is an estimator of something larger, and then this is it. Now, once again, the approach is pretty much the same. First you want to do is compute the population mean. Okay, how do we do that? Just like before, take all the numbers, add them up, divide it by the number of numbers, we have 14. Then we want to compute the distance between each data value and the population mean, which is what we're doing here, and it's just like what we had before. 14 minus 14, 0, squared 0, and so forth. At step 3, add them up. There we go, we have 10. And then finally, step 4, we divide by n, which in this case happens to be 5. And we have a population, there's a typo, a population variance, should be a 2 there, a population variance of 2. Okay, so that's everything we need to talk about relative to the sample variance and the population variance. The next thing we need to talk about is the standard deviation. And that is how much might we and that is a measure of how much we expect a number in the data set to differ from the mean. Okay? And to do that, that is just simply nothing more than the square root of the variance. And since we have 2 variance measures, we have 2 standard deviation measures. Notice the population standard deviation uses the symbol sigma, little sigma, and the sample standard deviation uses the symbol S. So this right here is the formula for the population standard deviation. And notice it is nothing more than the square root of the population variance. You want to find the population standard deviation? Compute the variance. Take the square root, done. All right, similarly, the sample standard deviation is nothing more than the square root of the sample variance. All right, so how do you compute them? Relatively straightforward. Suppose you want to compute the sample standard deviation for this particular data set. Well, the first thing you want to do is compute the sample variance. We already did that. Okay, then take its square root. Okay, it turns out the square root is 2.5. Of 2.5 is 1.5811, and this will go around to 1.6. Notice the rounding rule is still the same. Essentially, we will round to one more decimal place than the data values. Now keep in mind, however, that to do this, we don't do any rounding until we get to the end. Okay, population standard deviation, the exact same thing. First thing, compute the population variance. We already did that. That happens to be 2. Take its square root, and that will give us 1.4142, which will round to 1.4. Okay, so that is it for this particular video on computing the population, or computing our 3 measures of dispersion. Keep an eye out for a couple more videos. One will talk about how to do this using technology, which you really want to watch because that's how you're probably going to do it in your homework and your tests. And the other one will go over your homework problems. As always, if you have any questions, please feel free to contact me. This is Bob Boyle.